Any questions before we start? So someone did ask me a question. They sent me an email. Students love email. They love it. It says, "Hi Robert, I hope you are well. Thanks. I just wanted to find out how the first coursework is marked with respect to the timing. I have just completed the video." It's very early. "However, it is actually 2 minutes and 20 seconds long, and I am struggling massively to shave off any more of it. Is the 2 minutes a strict cutoff where nothing afterwards would be marked, or is it a general guide so that you do not receive any longer form videos? I would really appreciate some guidance here. While I have time on my side, I would like to know how this might impact my work." Is that the answer? Somebody giving the answer? So, in response to this question, I have posted a video. And the video is in Coursework 1. If you look at Coursework 1 and you scroll to the bottom, there's a special section called References and Extra Help. And there's a video here called 18 questions and answers on Coursework 1. So I've got 18 different questions there and 18 different answers. So you're welcome to have a look at that. And the answer to that question is in that video too. And I've also posted a copy of it on the chat for Microsoft Teams, this chat for the module. So the answer is yes, the videos are strictly limited to 2 minutes. For a few reasons, a few very good reasons. One is we have like 250 students or something in this class, so we have to restrict the length of time on the videos. But the second reason is that's even better is that's real life. Like you really only have 2 minutes to present something to some people, right? You only have 2 minutes. You're lucky to get 2 minutes of their attention. And this is a skill. This is a skill to force you. You can't force you to do anything. Encourage you to really focus on what you think the essentials are. What is the essential message? Because the longer the video is, the more stuff you include, and the more you defer this decision of what's essential and what's not essential. So it's really saying you must decide what's essential and what's not essential. Yeah. Any other questions? There are 18 questions and answers in that video. Just about Coursework 1. And that's not the only video. I have another video. I don't know if anybody noticed it from last year, but there's another video with a bunch of questions and answers on Coursework 1 that I will, it's already there on the last year's playlist. Okay. Another thing I'd like to point out is there's this thing called early module feedback. So you can click on this link on Moodle, and if you want to provide like anonymous feedback on the module, you can do that. Everybody is encouraged to fill out feedback. If it was up to me, you'd fill out, everybody would fill out feedback, and it would say something like, "I love this module, I can't get enough of it, I always look forward to the lectures, like this is the way every class should be," stuff like that. So if there are any questions or comments, feel free to interrupt me anytime. Also, for the early module feedback, you don't have to use that form. You can just tell me. You can just say, hey Bob, I would like to learn this topic, or I would like to make this change, or something like that. I would like to start, for example, I would like to start the workshop on Fridays at 8 a.m. instead of 9 a.m. That would be like some feedback, right? Or 7 a.m. So today we're going to talk about quantitative research methods. Some of you will be familiar with this material already, actually. So I think this is going to be easy. This is going to be an easy one, I think. So what evidence do we need? So we form some hypothesis, right, for our projects in research, generally speaking, or we're trying to answer a question, or we're trying to solve a problem, or all three, right? And then at the end, we say that we've addressed the question, we've tested the hypothesis, we've answered the question, we solved the problem. But just saying it is not enough. You have to provide some evidence, right? Show me the evidence, like that you really did solve your problem. So that's we're going to talk about one sort of way to address this, and it's using quantitative methods. Right? So usually there's an evaluation section, right? And it's in that evaluation section that we're actually focusing on today, right? You know that the type of evaluation is one of those essential elements of every research paper that you extract for Coursework 1. So today is kind of like a special focus on that section, right? Most evaluation results are comparative in some way, right? You might have written some software that's faster than previous software or more accurate, like AI, right, is obsessed with accuracy. Right? All the results in artificial intelligence are a probability. Like, what is the probability of this being correct? Right? Does what you've worked on solve new problems? Does it scale as input data size increases and so on? So you're always measuring your own results compared to someone else's. Sometimes there's a theory paper and we show a proof, but that's not what we're going to talk about. For many projects, the results will be statistical. You'll be asked to perform some statistics to support your hypothesis or your question or your claim or something like that, which means we may need to run an experiment multiple times. So that's what we're talking about, quantitative data today, quantitative methods. This word, you'll hear these words quantitative and qualitative a lot. They're meant to be very similar words, just to confuse you as much as possible. Quantitative data refers to numerical data that can be expressed using numbers. So that's what we're talking about today. Qualitative data is data that's expressed using natural language text, generally speaking. So quantitative data can be represented using quantities or numbers, or at least some categories. And we might have a collection of numbers as opposed to a single number. And we have lots of different types of numerical data. You might have studied this in mathematics, right? The natural numbers, integers, and real numbers, irrational numbers, complex numbers, all those things. We have numerical data, categorical data, ordinal data. And sometimes we try to use these approaches so we can measure things objectively, right? As opposed to subjectively, not based on our opinion, but based on something we can measure and observe. I can measure it and observe it, and then somebody else can measure it and observe it. And maybe there's an agreement, right? Remember our little statement on how the truth spreads and this idea of reproducibility? So we're looking for objective quantities or objective measurements, right? Measurements that don't depend on somebody's opinion and can be reliably measured. If we can derive some numbers, some quantitative analysis, we get a data set, and we can calculate statistics from these data sets. Statistics that are something that say something or describe the data set some way or summarize the data set, right? And then we can draw some conclusions about the question that underpins the data. So imagine in this scenario we have a data set that is a list of every house in a city and the price of that house, right? That's a common data set, isn't it? And then we can ask the question, are houses affordable in that town? Right, and then we can do some statistical analysis to find out if houses are affordable in that town. Right, we can get, for example, the median average, or the median house price, or the average house price, and then compare it to the median average income for a household, or the average income for a household, and make some judgment based on those statistics, right? The median and the average household income compared to the price of a house. We can use descriptive statistics using measures of averaging and distributing those to summarize different data sets and then comparing them, right? We can use visualization, right? We can show the data in an image, which is one of the topics we are going to study in this module, by the way. We will have a lecture on visualization. And we can use inferential statistics, saying something about a population by generalizing from a sample and saying how confident we are in that generalization. So today we're focusing on descriptive statistics, right? So we have a data set already given to us, and we want to describe it or summarize it. I like to use the word summarize, actually. So if you have a billion numbers, it's hard to look at a billion numbers, right? So it's nice to summarize those numbers somehow to get a summary. How do we summarize a large data set? We can do it using some statistical measures. We can measure an average, like what does the center look like? What's in the middle, right? What does the average look like, or what does a typical value look like? That's one way to sort of summarize a data set. And another way is to describe the variability of the data. So we have a central tendency, and then we have a variability. Is the variability small? Like, are all the data samples near the average or the median or the central tendency? Or are they spread out very wide? So these are two common statistics, the kind of trying to understand the center of a data set and also trying to understand the distribution, how much the data set varies from the central tendency. So when we're looking at the center of a data set, one of the common ways to do that is to look at the mean, so-called mean. Adding together the values and dividing by the length, right? So this is something everybody knows about. So whenever you summarize a data set, so imagine you're taking 1,000,000 numbers and you're computing the average. You're losing out something, right? You have a summary, but you're losing some information. And this is some information that you're losing. You're losing information about extreme values, right? And you can have a class like this, where maybe the average score on Coursework 1 is a 70, but you have one person that got a 0, for example, and then the average is shifted by, you know, a significant amount, right, because of one person. That can happen. One way to try to address that is using something called the geometric mean, the square root of the product of numbers, right? That's a distance, right? Particularly when you're trying to find a meaningful average for numbers that increase multiplicatively. Say that 10 times fast. So another kind of central tendency or a way to describe the center of the data set is this so-called mean, the middle value. So how do you derive the middle value? You sort all the values in the data set and take the central one, the one in the middle. Right? So we have these numbers here. We sort them, and then we take the median, right? And this is not distorted by a small number of large values, right? So it's not the same as the average, right? Hopefully I think everybody here has seen this before already, right? This is not really new information, right? Everybody's seen average and median before, I think. Mode might be something that you're not so familiar with, right? A value that appears the most often, particularly useful for categorical data where we can't add up or order the data. So if we have a data set and we want to find out which one appears most often, for example, mode 4 appears the most often, right? We can calculate the mode of this data set, few, few, many, some, many. So in this case, few appears very often, right? But it's not perfect. So all of the statistical methods, they're very helpful, right? Because we can summarize a large data set by just a few small numbers. But there are limitations, and there's information loss, right? Every time you summarize something, you're going to lose some information. Right? And sometimes it's difficult to understand how to interpret an average, right? What does an average crime rate? What does that mean, right? You could have lots of different interpretations of that. So there are times when to describe a single data set or a single group with one average is not really a good strategy, because you might have subgroups, right? Very common at the university here when we're calculating grades, we subdivide the classes, for example, into undergraduate and postgraduate students. We don't put them in the same groups. We don't treat them the same. We want to see two separate groups. So we don't have one average for both groups. We have an average for each group or each subgroup, right? That can happen a lot. This is another limitation of statistics, right? So we just talked about average, mean. We didn't talk about standard deviation yet, but if you look at these are all data sets, right? We can look at each one of these. They're all data sets. They're all scatter plots. They're all a set of data samples, right? But they look very different, don't they? They don't look the same. It's because they're not the same, right? We can see that they're not the same. This is an example of visualization, right? When we see a scatter plot. But if we compute the statistics on them, like the average and the mean and the standard deviation, they're all exactly the same. They all have the same x mean, the same y mean, the same x standard deviation along the x-axis, the same standard deviation along the y-axis, and so on. So imagine summarizing this data set and this data set and then thinking, oh, well, they're the same because they have the same average and the same standard deviation. You'd have reached a false conclusion. Right? This is a famous example. It's called the Data Source Dozen. And you can even download the CSV file to generate those images. Right? So it's just something to be aware of. Statistics are very good and they're very helpful, but they don't tell the whole story. If you want to understand your data in a better way, like in a more thorough way, you need visualization. Right? You need to see it. You can't rely only on statistics, right? Has anybody seen this before? The Data Source Dozen? Anybody? No? Nobody's seen it before? It's interesting, isn't it? It's kind of surprising. It's a good thing to know about. Very good thing to know about. Like now that you've seen it, your education level just went up significantly. Like I just saw it. So we talked about, like, so far focusing on the central tendency. Now what about the variability part? That's the spread. Like how much do data samples deviate from the central tendency? We can measure variability, right? Right, 3 different data sets that have the same average, but they are clearly different, right? These 3 have the same average, but their spread, their distribution is different. Right here, we can compute something called the standard deviation. Here it's 7.9, 15.8, and 31. So as the data varies, the more it varies, so does the standard deviation, so-called standard deviation. By the way, these are all histograms. Does everybody see that? This is a histogram, this is a histogram, and this is a histogram. So a standard deviation measures how varied data set, or it gives an indication, it summarizes, it's a summary of how varied the data set is. For so-called normally distributed data, around 68% of the data are within 1 standard deviation of the mean, over 95% within 2. So this is what it looks like, 1 standard deviation. This is the histogram of data samples, right? And this is what 1 standard deviation looks like. And this is what 2 standard deviations looks like. It makes a lot of sense, by the way, as soon as you can see it. If I was just using text and I didn't show you any images, it would be much more difficult to understand. But as soon as you can see it in an image, suddenly it's much more understandable. So, all summary statistics have some limitations. And here's one. What if the data is so-called multimodal? There are multiple peaks in the distribution. Right? Here's a data set with 1 peak and then another peak. We'll only see that if we visualize the data. We won't see that by computing the average and the standard deviation. Okay, so for a lot of data, there's a variability, but there may be some other factors involved, like if we're talking about measuring the properties of an animal species, there might be some subgroups again, right, that are distinct, and we don't necessarily want to lump them together. right? There might be uncertainty associated with the variability, right? A lot of surveys are based on this so-called Likert scale, where people say that they're very satisfied, satisfied, or not satisfied. That's very subjective, right? And sometimes we might be studying something related to health, and maybe the standard deviation, computing the standard deviation alone is not something that's very helpful, right? So we can try to use some statistics to help us understand if there are meaningful subgroups within a data set, right? Or if we want to compare two groups with each other. For examples, do penguins of different species have different average heights? Those might be some questions we want to ask. Are math students happier on average with their course than computing students? Does a new antibacterial drug work better than the established one on average? So in all of these cases, in all of these examples, there are two groups being compared to one another. And we're trying to measure how they compare, and if we're making progress, let's say, or one group is better than the other, or somehow different than the other. And there's always, in all of these examples and in all of these data sets, there's always some variability, right? So in the case of a penguin, we might have an average height of 450 millimeters and another average height of 350 millimeters. And can we draw any conclusions about the two subgroups based on the averages? Is that possible? Is it valid? If I take a survey and I find out that 61% of math students are happy with their course and 60% of computing students are happy, is that the same? Can I draw any conclusions from that data or not? How do I compare those two groups and try to measure some confidence with my comparison? So in both cases there is a difference, but is it a so-called robust difference? Can I be confident? And we're talking about inferential statistics. We are inferring something about patterns in a whole population from a subset known as the sample, right? So in order to try to study the difference between two groups, we can use another statistic that I think everybody here has heard of, statistical significance. Everybody's heard that term before, I think. I think it's hard not to hear about that term. Statistical significance asks, roughly speaking, could the differences between two groups of data be down to chance? So what is the likelihood of the difference between two sets of data just being a coincidence or by chance? That's essentially what we're trying to quantify, by the way. We're trying to come up with a way to quantify our confidence in assessing the difference between two sets of data. This is about so-called robustness. Another word is reliability. I like the word confidence. Like, we're trying to measure our level of confidence in our conclusions about, are these two subgroups different from each other, or is it just a coincidence? So an effect can be small but still be statistically significant. Say that 10 times fast. So if a drug A clears an infection reliably between 80 and 82 hours and drug B reliably between 83 and 85 hours, the difference is statistically significant, but probably not so important, right? So you can have two groups of data sets that are very similar. There's only a small difference, but it still can be a statistically significant. In most cases, there's some overlap between the two groups of data, so we have to figure out, okay, is the overlap, how significant is the overlap, and how distinct are the results from each other? Or is the distinctness between the results significant? Can we say, draw any conclusions with confidence? That's really what we're trying to measure here. Probably everybody's heard of like p-values before. P-values in statistics. Yeah, exactly. That's where this is going, like coming up with this so-called p-value, a discussion of p-values. So imagine we have two groups of data, and we want to look into it, investigate it a little more. Is the mean of group A different to group B? And if they are different, is it an accident that they're different, or is there some underlying cause of their difference? And can we say with confidence, can we reach a conclusion with some level of confidence using statistics, right? So the standard approach is to define two situations or two outcomes. One's called the null hypothesis. The null hypothesis is there's no difference between the two groups or the two means of the two groups, right? They're the same. There's no significant difference. You'll hear that phrase a lot, by the way, the null hypothesis. You hear it over and over again in statistical analysis. So the other hypothesis is the opposite of the null hypothesis. There is a difference. So the alternative hypothesis is there is a difference between the two means or the two groups, right? Other possibilities include, is the mean of group A significantly bigger than B? Or is the mean of A significantly more varied than group B? Right? Those are more statistical analysis that we can apply. If we focus on just the mean, we can perform something called a t-test to measure our confidence. Right? We have this hypothesis, like they're the same, the means of the two groups are the same, or they're statistically different. We can perform this test called a t-test to try to quantify the answer to this question. Right? The null hypothesis means that the two groups are the same. The alternative hypothesis means that the two groups are different. So to test that, we can use a two-tailed t-test, or one is bigger than the other, which is a one-tailed t-test. Which kind of test is appropriate depends on the question. So if we're just comparing the two groups and we're trying to figure out if there's a difference, we can use a so-called two-tailed t-test. If we want to find out if one group is, say, bigger than the other, or faster than the other, or more accurate than the other, we would use a so-called one-tailed t-test. So this is what the formula for a two-tailed t-test looks like. This is one of those statistics that you see very, very often. Right, X is the mean of the first set of samples, subtracting the mean of the second set of samples, so we get a difference over there. And then we take the whole thing and we divide it by this operator. S1 is the standard deviation of the first data set squared. S2 is the standard deviation of the second data set squared. And we divide both of those by the number of samples in the first data set and the number of samples in the second data set. And that's like the statistic, or that's how you compute the t-test. And it's a measure of confidence, right? Try not to forget that it's a measure of confidence. Now, I put a link to a YouTube video that goes into more detail about this. It does a better job of explaining it than I did, right? So I encourage you to look at that example. It will go into more detail. It will use more illustrations. You know, it will cover more material, more content. So for a given level of significance, we can calculate a critical value based on the number of samples, and then a t-table can be used to look up C, right? And this is our measure of confidence, right? This critical value is our measure of confidence, right? We compare T and C. If T is greater than C, then we can reject the null hypothesis. That means the null hypothesis is not true, right? The two groups are not the same. If T is less than or equal to C, then we fail to reject the null hypothesis. In other words, the null hypothesis could be true. Yeah, strange way to word that, but that's the way the wording is. So there isn't enough evidence to reject the null hypothesis. So we can't draw any conclusions with confidence. That's another way of saying that. And this is a nice little diagram because it shows the data, right? We can see some data and we can see, oh, there probably is something going on here, right? If we have a histogram, for example, where flipper length on the x-axis and then how often that flipper length appears, and then we have 3 subgroups. Well, as soon as we look at the data, we can draw, we can increase our confidence that there probably is something going on here that's not due to just chance, right? Right, if we compare the mean of this data set with this subgroup and this subgroup, we can be confident that there is a difference between those 3 groups, right? So this is using Python, by the way, to compare the groups, right? So some of you will use Python or will have used Python, and you can compute all of these statistics using Python, right? That's one way to do it. So here we have the group 1 data, the group 2 data, and then we have the group 1, the mean, right? And then, so there's the mean, and then we can take the square root and so on. So we can actually compute all of these numbers in Python, right? So that's just an example of computing a t-test in Python. So there is an assumption in the t-test that the data are approximately normally distributed, right? That means they have that Gaussian distribution, that with the one peak in the middle. That's what normal distribution. That's not always true, right? The distribution could look like this, right? That's not a normal distribution. This is something close to a normal distribution, but this is definitely not a normal distribution. In that case, there are more statistical tests that can be applied, right? Non-parametric tests that we don't look in, we won't discuss here. And then no discussion of statistics would be complete without a discussion of p-values. By the way, this is a very brief introduction and overview to some of these quantitative methods. Really, we should have, like a normal circumstance, you'd have an entire module just dedicated to statistical methods and quantitative methods, quantitative research methods. But here we're trying to summarize that. We're just trying to give you an introduction in one lecture. But in other circumstances, you would take a whole module. Has anybody ever taken a whole module of statistics or quantitative methods? One person? Two? Okay. Where did you take the module? What degree course was that? Last semester. Okay, good, good. You guys also take it last semester? Okay, pre-masters. Good, good. I should have had you guys give this lecture. We can convert the t-value into a p-value. So the difference between a t-value and a p-value is normalized. So rather than having an arbitrary spread or min-max value, you have a min-max value from 0 to 100%. That's a p-value, right? So it's just normalizing the t-value. So here it says we rescale it so that it's based on a probability scale. In other words, from 0 to 100%, or 0 to 1. So for example, if p is less than 0.05, then we reject the null hypothesis. This is very, very common, by the way. You'll see this a lot. And then, like, there's a big discussion about p-values and how valid they are, and we won't get that into that here either. I'm not an expert at p-values and statistics, so we won't get into that discussion. But anyways, the most common way to report statistical significance is to report the p-value. This is the most popular way of reporting the confidence of your results, that they're not due to just chance. This is the most common way. Right? And there are ways to perform experiments, like you could say many experiments are performed over and over again until you get the results that you want. You could do an experiment 1,000 times, right? And 999 times you get the results you don't want. And then you perform the experiment 1,000th time and you finally get the results you want. And then you report those results and you ignore all the other ones. So that's a common anecdote in science, right? So sometimes that's described using phrases like p-hacking or data dredging. And if you want to learn more about that subject, there are links to lots of literature on that subject. So for example, we can look at these graphs, and then we can, just by looking at these graphs, we can think, oh, there must be a relationship between the number of people who died by becoming tangled in their bed sheets. So if we were to judge the confidence in the difference between these two data sets using p-values, we might find that they're closely related to each other, but in reality they're not. Does that make sense? So you can draw false conclusions from statistics. It's possible. It's possible. Here's another example. So it's the total revenue generated by arcades correlated to the computer science doctorates awarded in the US. They look like they're correlated, and statistically they might be, but in reality they're not. They're not. It's just another example. And another example. Okay, so just to summarize, today we were talking, we gave just a short introduction to sort of quantitative methods for research, right? We discussed central tendencies, variability, and then comparisons between subgroups. And that was a very quick introduction, like a very quick overview, quick introduction, just to like warn you, you're going to run into this when you write your thesis. Like a lot of you are going to be asked to perform some statistical analysis during your projects, right? You'll work with your supervisor. Your supervisor will tell you like what they want to see. Like, I want to see this statistical analysis with this data, and I want to see this result, and so on. So you'll find out more when you're actually working on your project. By the way, when I'm trying to understand statistics personally, I don't look at slides. I look at YouTube. Anybody else look at YouTube for statistics? The people that took statistics, did you look at YouTube at all? There are some extremely high quality YouTube channels just for education on statistics. Some of them are very, very high quality. Like, they go into a lot of depth. They give a lot of illustrations, which are very helpful, and they go step by step into the details. I just picked out one of them here. But like, if you were thinking, how do I didn't quite understand Bob's explanation of the t-test, you could look it up on that YouTube channel and you'd find really, really detailed, very illustrated, well done explanations of t-tests. So I encourage you to have a look at that. StatQuest is another is a YouTube channel that's really high quality and goes into really, really depth on that. Any questions? Okay, we will stop. You're free to run, jump, and play.